Well, good day, everyone. Welcome to the webinar SPES Particle Characterization Method Game Changer for Biobased Nanomaterials. I will soon give Tiziano Sanvito the online stage. He's the inventor of SPES and the director of EOS. Your questions, please drop your questions in the question box. And afterwards, I will ask all the questions you have about the presentation to Tiziano. But I will let you start first, Tiziano. Thank you. I think you're...
For sure. Thank you very much.
Thank you.
It's a pleasure to be here. Thank you. Thank you very much. I'm Tiziano Sanvito. I'm the sole administrator of EOS. I'm a physicist by study, and during my studies with some colleagues, we developed from scratch the SPES method for the analysis of particles in fluids. It is a novel approach, thanks which we are able to characterize particles in a novel way. We are able to retrieve more information on single particles in a fluid. And today I will present you the application of the method to the analysis of particles in liquids. Especially, I will present you Classizer 1, which is the device based on this novel method for the analysis of particles. Just a sketch of our history. EOS started a few years ago with the mission of enabling the scientists and the researcher in the analysis of particles, the quantification of particles, in the characterization of particles in mixture of simple and complex particles, also in heterogeneous fluids for biological, industrial, and environmental applications. We have patents, we have different applications, we have different validations, and we started the commercialization of the device since the 2019. Today, we are represented in Europe by several companies, and in the Benelux area, Inventec is our local partner for distribution and technical support. But let's start. Why measuring particles? Because essentially many particles are present in many fields, starting from pharma, life science, pigment, cosmetics, and so on. And rephrasing the sentence of Lord Kelvin, if you're not able to measure particles, you are not measured to improve the formulation based on particles or to improve your knowledge about your products. So it is essential to characterize properly the particles in the liquids. So how we can measure particles? Today, there are different applications, different methods capable of providing information of particles in fluids. Let's say that we have the satellite scattering, the single particle scattering, dynamic scattering, nano-tracking analysis, but also non-light scattering based method, for example, Coulter counter and direct visualization. But what is the limit of traditional approaches? Why we are presenting a new method? Because they suffer a huge limitation when you have to measure complex system. And with complex system, I mean mixture, for example, in simple fluids as well as in heterogeneous fluids where there are other kinds of particles. Because in these systems, everything shines light. So the system, traditional approaches cannot discriminate signals coming from the particles of your interest with respect to other kinds of particles. Why this? Let's consider the satellite scattering, just to give you a sketch about what I'm saying. In the satellite scattering, you have a system of particles in a liquid flowing through the device. A laser is employed to illuminate the particles, and the system measures the intensity of the light scattered at different angles. And from this information, and thanks to an information about the nature of the particles, let's say you have to set the refractive index for the whole system, this kind of approach provides to the user the mean or the Fresnel for particle size distribution. So provide any information, a single information, which is the particle size distribution, considering all the particles as if they were the same type in suspension. You are not able to discriminate more population or a mix of particles. The same if we consider, for example, the single particle approach. Let's say obscuration, just to give you an example. We have particles, we flow them through a cell again. But in this case, we focus the analysis on single particles. We measure in particular the drop of the transmitted intensity due to the transit of the particle through the beam. Then we have to apply a calibration curve to interpret the drops of the intensity. Typically, the calibration curve is related to a well-known material, for example, latex spheres. And then the device provides to the user the particle size distribution, considering all the particles, again, as they were of the same time of the calibration. So you measure all the particles as they are polymer. But that's not true in mixture, because you cannot interpret all the signals as they are made by the same material. And as the latter but not the least example, let's consider dynamical scattering. We have the particles in a vial, they move to the Brownian motion, we align the particles with a laser, and we study how the light at a given angle fluctuates in times due to the Brownian motion itself. And from this information, an inversion algorithm is applied, and the device provides to the user the hydrodynamic particle size distribution, considering again all the particles as the same. You cannot interpret the particles in terms of composition, in terms of internal structure. Moreover, the typical particle size distribution is the intensity. If you have to retrieve a quantitative information about the particle size distribution, for example, the numerical concentration, you need to set a refractive index again. So you have to consider all the particles as they are made by the same material. So we continuously have the same limitation. So if you have a system, very simple system made by same particles with more or less the same structure, same optical properties in suspension, you can rely on traditional methods and they provide you a size. But it's a mess to measure complex systems made by mixes, a mixture of different kind of particles, of engineered particles with a structure. If you have to derive information about the behavior of the particles, for example, an aggregation ongoing, or the inclusion of something inside the particles, a particles-to-particles interaction, or even if you have to measure how particles behave in a heterogeneous matrix where other kind of particles are present. For example, if you want to understand which is the best formulation to have a given delivery, for example, in unfiltered blood, where other kind of corpuscles, for example, the cells, the platelet, and so on, shine and then can create a strong signal in the scattering. We focused on this. This is the need. And we developed a new method capable of it. We have how it works, very simple. We have a sample. We flow the sample using a pump through a cell, and we analyze the particles with a special focused beam. And we study how the particles shine in the forward. Or in a more precise way, we measure the interference between the scattered light and the transmitted light on a segmented sensor in the forward. What happens? When a single particle transits through the beam, a system of fringes arise on the sensor. And from the analysis of the system of fringes, we are able to define at least a couple of independent parameters of that single particle. From the dark fringe, let's say we are able to derive information about extinction. In particular, we are able to quantify the extinction cross-section of that particle. From the visibility of the fringes, let's say the bright one minus the dark one, we are able to derive information about the scattering, let's say information about the polarizability of that particle in a quantitative way. Plus, we count them because we count how many signals we observe per second, so how many signals are present per milliliter. So we provide a quantitative information about the numerical concentration of the particles. So it is natural to measure a huge number of signals and sum them in a histogram, which we call the Gauss clouds, where particles are located depending on their optical properties. Let's say the extinction cross-section versus the polarizability. And if we have a system made by different kinds of particles, if the optical properties of the particles, as in this example, are different clouds are identified in the map. So the user can measure the system as a whole or select a single portion of the map, measuring the information of and retrieving the information on a single population of particles in the fluid. So in the case of an heterogeneous system, we are able to classify the particle populations present in the liquid, and during the analysis, the user can measure them independently and can separate the signal, measure how many particles per milliliter there are of each single population. This can be done offline, but also inline, for inline online continuous flow analysis, for example, with 1 second time resolution, to monitor the transient and the behavior of the particles in time during a process, for example, the appearance, for example, of a secondary population related to scraps, or the modification of a population due to the synthesis of a given particle population. Principal component analysis and other statistical approaches are suitable for the analysis of batches, for example, for the batch-to-batch analysis, and many other kinds of nice tools can be developed and applied to this kind of information. But for sure, this is the first step. So this is the interpretation and the classification of the particle populations on the basis of their optical properties. But we can apply also models. For example, depending on the position of the clouds in the map, we are able to identify the best optical properties of that sample. For example, we are able to provide, and the system automatically provide, the effective refractive index of that population in the middle of many others. So the user can select a single population and retrieve, for example, the particle size distribution of that population. In this case, we can select the small population here and retrieve the particle size distribution, the concentration, and all the statistical information, the wear size analysis, for example, and so on, of this population, regardless of the presence of this elongated and broad population here. So we are able to manage and face very complex systems. Just a few examples. This is a very academic example, alpha of a micron polystyrene. As you can see, we have a model SPES system, a very narrow population here appear on the two-dimensional map. The system interprets the population considering some tailored ME approaches, and so the red line is drawn on the map, providing to the user the information about the best optical properties which describe this kind of population. This red line corresponds to a refractive index of 1.58, which is an agreement with the expected optical properties of this kind of particle within experimental error. We count how many particles there are per milliliter, so it is a quantitative information about the number of particles per milliliter with a given optical property, and all this information about the sizes are provided as well to the user. The technical feature, let's say, of SPES are the following. We are able to measure particles starting from 100 to 100 nanometers in diameter, depending on the material, up to 20 microns in diameter. The typical particle size concentration, the particle numerical concentration, is from 10 to the 5 up to 10 to the 7 particles per milliliter. The lower one is suggested just to not waste too much time, but you can apply the method also to measure very rare events or very, let's say, diluted system without any issue. It is just a matter of statistics, so time of acquisition. The upper one is demanding to avoid the so-called pile-up of the signals. Since we have to measure single signal, so single scattering even from single particles, we want to avoid the presence of 2 or more particles in the same time in the beam. The system is very robust. It applies pulse shape analysis and rejects the data coming from spurious signals. But to guarantee a high robustness to the data, we suggest to not increase the concentration of the system above this limit. But consider that the system provides to the user information in real time about the concentration, so it provides to the user an information to manage and tune the concentration of the system in real time to avoid this kind of issues. The typical measuring time is, let's say, some minutes, 10 minutes, 50 minutes are more or less enough for measuring most of the samples. For a mono SPES system as this one, a couple of minutes is enough. It's just a matter of statistics. And with statistics, I have to say that we measure typically 10,000 particles per minute. So this is a reference for the concentration, the statistic of the sample at optimal condition. The wet surfaces of the device are very good in terms of chemical compatibility. They are made of from quartz and PIC, but depending on special user needs, we are able also to tailor the materials. We can modify the fluidics and rely on steels, and we can modify and rely on different polymerics tubing and so on. So we are able to customize the system if needed. The sample flow typically start from 0.1 ccm and range up to 4 ccm, so 4 milliliter per minus. These are the typical range flow, sample flow range, but also in this case, changing the fluids, we are able to tune the sample flow range. We are able to measure also higher flow. So depending on the application, we are able to manage the system and provide you the best solution. We have different example of validation in terms of the size accuracy. Here I present you the particle size distribution of different latex samples and are all in agreement with you, few percent with expected position. The repeatability of the device is very high. If you try to plot the 16 particle size distribution of 16 replica of the same sample, you obtain something like this. So the system is very robust if the sample and the system is stable in time. Otherwise, we are measuring the instabilities of the sample during the time, during the preparation. And again, we provide information about the concentration. So you can measure the numerical concentration of the particles in time, or in absolute way or a relative way. So you are able to quantify the numerical concentration of a given population of particles in the fluid, or to measure the relative concentration between two populations. For example, in the formulation you have an excipient and API, you want to be sure about the relative concentration between the excipient and API at a different stage of the formulation and production. All this information can be provided inline online, but also offline for any kind of analysis and data treatment. Considering some of the advantages of the method, let me show you this example. This is data coming from the analysis of a mix of system, a mix of polystyrene and PMMA, both with the same size. If you try to measure the system of polystyrene and PMMA mixed with the same size, you cannot determine the presence of two different kinds of polymeric particles with traditional method, because they more or less lies in the same area. So using, for example, a static light scattering, you obtain a large particle size distribution, but you are not able to resolve the presence of two different kinds of systems in the same vial, for example. Thanks to the SPES approach, you are able to do that. In particular, in this case, as you can see, two clouds of data are generated and plotted on our EOS clouds histogram. Each single cloud of data lies in position compatible with a different effective refractive index. So the system provides to the user information about the different nature from the optical point of view of the particles, a quantification about how many particles of polystyrene there are, how many particles of PMMA, and if you select a single population, you retrieve also the particle size distribution of that single population, regardless to the presence of the second component. The same information can be retrieved if you mix a polysper system with a monosperse one as a reference. In this case, I present you the data coming from an emulsion of silicone oil plus a monosperse system of half of a micron polystyrene spheres. In this case, we are plotting the red line. The red line is an uncalibrated theoretical lines related to the silicone oil emulsion. As you can see, we are able to describe very well the position. So the SPES method work with uncalibrated data. We compare the theoretical expected position to the measured experimental data, and we are able to provide information this way. For example, focusing the analysis on the secondary population of polystyrene and provide to the user again the particle size distribution and all the statistical information related to that population in the mix without any purification, filtration, and so on. So we are able to follow how it happened to this kind of a formulation. And some sketch about the possible layout of the system. The system is a benchtop device, but can be used in different ways. Let's say the most easy one is to measure the sample inside the vial or a cuvette, for example. To do that, we have to flow, typically in a pull system, the sample from the vial through the machine and through a drain. This is the most common layout and setup. You can rely on peristaltic pump, high quality peristaltic pump, as well as syringe pumps. In this case, we have a peristaltic pump. As you can see, we have a sample here to be measured. It is an ink. We pull the liquid through the device and then go to drain. In this case, we rely on a couple of syringe pumps to create a push-pull system and flow many times the same system through the device to gain more statistics with a limited volume of sample. But we are also developing accessory for these purposes, for example, auto-sampler as well as sample manager. And if needed, if the time is demanding, this system can provide a useful effort, a useful support for sample management and sample analysis operation. For example, providing the automatic dilution of the sample, the cleaning in automatic way the system, and the setting is prevented automatically using different stirrer. So they provide a very nice way to measure many times, increase the throughput of the system without any effort from the point of view of the user. But again, the system can be also tailored based on the single user need, if needed. This can be useful for inline-online control of particles in fluids, but also for the coupling of the system to other kind of devices. For example, to look for synergies between our system and traditional methods already present in market, already present in the laboratory of the user. For example, we can couple the system to FFF separators, commercial FFF separators, as well as a spectrophotometer and so on, to provide information and useful way to interpret the traditional data coming from spectrophotometer using our data. I will present you in the last part of this seminar some results about this. But we can provide also sensor able to match and couple with more complex situation and more complex setups. So if you have a special need, probably we have a special fit for that. So feel free to ask to us whatever you like. If we are able to support you, it will be a pleasure. But let's start to provide you some information about possible applications and focuses on biotech ones. You know that biotech products can be in different shapes. Let's say you can have tablets, powder, capsules, screens, liquid solutions. Maybe you have to check how they behave in the environment, and sometimes you have also them in aerosol. But let's focus on the first situations. We have to focus on this typical problem. We have a formulation, we have a mix of particles, and we want to characterize them. And we want to obtain information about the single population regardless of the complexity of the system. We don't want to have a whole general information. We want to be precise and accurate in the analysis of this kind of particles to improve the formulation, to improve the quality control, to speed up the research. And we can face different situations. For example, we can have a mix of homogeneous particles. We can have a mix of heterogeneous particles, but with an heterogeneous inner structure. We can have core shell system, mesopore structure, more complex situation. But we may also have to define the best formulation, looking at how the particles behave in the final liquids. For example, looking to releasing from the point of view of the carrier, to aggregation, to absorption of water, to degradation, to internalization of the particles by cell, to interaction with the surrounding media. There are different complex situations that can be managed using this device. Let's start with the first case. We have a formulation which is made by a mix of different kinds of particles. Let me show you a representative results considering a probiotic commercial product that can you take from the shelf and measure it using our device. This is the case of Bacillus clausi, which is a probiotic product for the management of imbalance of intestinal bacterial flora. If you look to for example, to this kind of probiotic, they declare that you have to find in suspension 4 to the 9 spores in the 5 ml. So an expected final numerical concentration of 8 to the 8 particles per minute. If you try to measure this with traditional methods, it is quite difficult to obtain the right information and the right quantification of probiotics. You have to rely on different approaches using, for example, fluorescence or other kind of stuff, but you have to modify the system. Using our method, you obtain this kind of information. As you can see, two populations are observed. One in this position where I move the arrows of the mouse, and another one in position. And if you check the formulation of this kind of products, you will read that there is also a population of microcrystalline cellulose in suspension with a typical refractive index of 1.5 at our wavelength. In the yellow one, for example, at 90 degrees, but also considering very close to our wavelength. So how you can manage this? You can select the first population. The first population is compatible with an effective refractive index of 1.41, which is close to the expected one for this kind of Bacillus clausi. And the numerical concentration of particles inside this closed area is 8.1 to the 8 particles per milliliter, which is the expected concentration of the Bacillus clausi. And moreover, the particle size distribution of the particles inside the closed area, considering the measured effective refractive index, are in agreement also with expected sizes of this kind of corpuscles. So you are able to measure and quantify the particles, let's say the spores, also in presence of excipient typically. But you can also focus on the analysis to the excipient. In this case, we are focusing to the microcrystalline cellulose. As you can see, the effective refractive index measured is very close to the expected one from the literature, and we are able to quantify them and size them. So we are able to manage the complexity of two populations in the same formulation, regardless to the fact that they are very close in size and very close in concentration. We are able to separate the components. But this kind of information can be obtained also in case of heterogeneous structures. For example, you have to deliver something. You can rely on PLGA as a polymer, polylactic glycolic acid. You maybe have to internalize something, or you have to create a cold shell structure to internalize something. In the three cases, you have to modify the structure. But if you try to quantify and size the particles using traditional approaches, for example, the DLS, you are not able to obtain relevant data about the structure because they provide you information about the whole particle size population. But they are not sensible to the inner structure, or using, for example, static light scattering, you have to provide the refractive index. So you are blind in the respect of the inner structure of the particles. You need more. And the more comes from the SPES approach, because since we are sensible to the extinction cross-section as well as to the polarizability of the particles, in the case of a change of the structure, for example, here including curcumin, or here including a liquid core inside the particles, we are changing the effective scattering properties, because the effective properties depends on the whole particle, not just on a portion of it. So we are able to measure the pure PLJ and appreciate in a quantitative way the difference of the pure PLJ respect to the emulsion of PLJ with curcumin, or the double emulsion with the liquid core, so the core shell structure. And this can be retrieved judging the position of the barycentrum of the two-dimensional distribution in our map, changing the structure of the particles. Because if you change the structure of the particles, you change the optical properties. So if you are able to measure the optical properties, you are also able to interpret the change in the structure of the particles and follow what is happening in the formulation, changing, for example, the osmolarity, the pH, and so on, different the surfactant or other kind of chemical treatment and so on about your sample. You can also monitor, in case of biomarker, these are biomarkers made by gold, the size and the shape of this kind of particles. For example, if you rely on metallic particles, we benefit from the surface plasma resonance to enhance the differences between the different particles. So we are very sensible to small difference in terms of the size, but also difference in terms of the surface shape, the roughness of the surface, and so on, because these kind of changes change and modify the optical properties of the particles. And you can monitor these in real time. So if you have a closed loop synthesis reactor, we are able to provide information about the concentration and about the characteristics of the particles without any purification or filtration. So in presence of scraps from the synthesis, in presence of droplets of oil or emulsion if needed during your process, we can manage complexity. Another example for biotech application is the following one. You are formulating an emulsion of PLJ. You want to check which is the best one to have a given release in time. And you want to monitor this not in a simple liquid which mimic a biological liquid, but you want to measure it in a real biological liquid, for example, the human serum. How manage this? Because you have the natural corpuscles of the serum in the surrounding, which can affect and change the scattering properties of the whole sample. Let's say you cannot measure the effective particle size distribution and the effective stability of your particles in the middle of many things which scatter light. Let me show you an example. In this case, I'm presenting you the particle size distribution and the two-dimensional EOS clouds of an emulsion of PLJ in a PBS. This is the reference, let's say. This is the standard system. And let me show you the two different cases. A first one of an emulsion of PLJ and the second one of an emulsion of PLJ with a stabilization via PEG. We are looking to difference in terms of stability in time. So we incubate the particles in human plasma and we can measure the characteristics of the particles. This is at 0 time, 0 hour. As you can see, if we take an aliquota of the incubation of particles in human plasma, we dilute it and measure it, we are able to appreciate the presence of two populations. A first one related to the contribution of the PLJ particles, and the second one broader related to the biological corpuscles in the human plasma. So we are able to check the presence of two different kinds of population, and we are also able to verify that the samples, the two samples, behave the same at 0 time as expected. But after a day and after a couple of days, the particles without the chemical stabilization, let's say the surfactant, change their nature. As you can see, using this red line as a guide for your eye, they move from this line, which is the expected position for compact spheres of PLJ, they move to an area corresponding to a lower refractive index. So this means that they are changing their nature. In this case, they are absorbing water. So the structure of the particles change, they become mesoporous from a physical point of view. The liquid in the surrounding penetrates inside the particles and lower the effective refractive index of the whole particles, because it is an average between the polymeric and the liquid inside the particles in this case. But thanks to the optical properties, we are able to observe that the particles are not more stable, so they change. So in case of an API inside the particles, the API is released in the medium. So we are following the stability of the system, looking to the carriers and how the carriers behave directly in the fluids. And what happens if we measure in the same way the system with the surfactant? We are able to check that the particles are more stable and the change behave after. Let's say they show us a change in terms of the optical properties after a couple of days, not after a single day. So this means that we are able to follow the behavior of the particles in this complex system. And we are able also, thanks to this tool, to define the best formulation to have a given release in the target media. For example, you have to define which is the best formulation. You can try them directly in the final target liquids, regardless of the complexity. And you can judge the best formulation, the best chemical or mechanical treatment on the basis of the results in the target fluids, not in simple ones. And we published also papers. There are many references on our website about the capability of the method to identify and monitor particles, also in very complex system as unfiltered blood. So in case of very complex system, you can measure particles, also in that cases. Let me show you a very complex system as a reference. You want to monitor how particles behave, maybe in a complex biomatrix as a cell lysis or in a cell culture. You want to check how many particles are uptaken by the cell, if they are stable, And this information are essential for formulation as well as analysis of the selectivity from the cell, about the particles, about toxicological, cytotoxicological and ecotoxicological analysis, and so on. So how we can manage this? Let me use a couple of systems just as a reference. Half of a micron polystyrene and 1 micron polystyrene, and a mix of the two, of course. And we consider a cell line of V79. So we feed the cell with the particles, and after a proper time, we take the supernatant and measure the supernatant. As you can see, there is a very broad component related to the corpuscles in the supernatant, but also we are able to appreciate the presence of the particles of half of a micron polystyrene at this concentration. We are able to observe the presence of 1 micron particles in the supernatant, but also the presence of the two. So in this very complex system where there is a huge mass of particles, different kind of particles, different kind of biological corpuscles, plus a mix of 2 different kind of polystyrene spheres, we're able to resolve the presence of the 2 particles of interest, let's say the 2 nanoplastics in these cases, quantify them, size them, regardless to the presence of a very broad population and contribution from the surrounding liquid. But now we have to face something more complex. We want to check if the particles are inside the cell. How we can do that? We can take the cell, we can clean them in a very proper way. We can then lyse them via chemical or a mechanical approach. In this case, we via a chemical approach, so dispersing them in a mix of SDS and Tritonix 100. And then we can measure this, let's say, system, just diluting it. So no purification or filtration. As you can see, the complexity of the data is higher respect to before, because we have all the corpuscles of the cell, the fragment of the cell, the inner structure of the cell, plus we have the particles, plus we have the surrounding particles, biological components, and so on. But the most important thing is that we are able to appreciate the presence of the particles, for example, a small population of 1 micron here of polystyrene, again also in the mix, but also we are able to identify that there are half of a micron polystyrene particles, but they are not more stable because they are not more in the same position than before. So it is more or less like a puzzle. Where are the particles of interest? In the liquid are in this position, in the supernatant are in this position, but inside the cells are in another one. This means that something happened. They interact with the biological component. They are surrounded by biological material, for example, protein corona. This means that the average refractive index, the effective refractive index of the whole particles decrease because we have a contribution from the surrounding biological matter, which decreases the contribution of the whole particles. So it is an average between the polymeric core and the surrounding core. So we are able to identify differences. But differences can be observed also in environmental releases. For example, we have a biological system, a biotech system, and we want to develop using some biotech application a sun protector, a new kind of sun protector. We can consider this case, which is a sun protector made by lipid nanoparticles with some zinc oxide nanoparticles inclusion. So we have, let's say in the end, a carrier made by lipid with zinc oxide inclusions. And we know that the refractive index of the lipid is 1.43, and the refractive index of the zinc oxide is more or less 2 at our wavelength. And we can verify this measuring the, let's say, poor lipid particles in the fluid or zinc oxide particles properly stabilized and dispersed. But what happens if we have to measure this system? We can check how the particles, for example, behave in target relevant media, for example, fresh water versus seawater. We have a biotech system. We have a dermocosmetical product. We want to identify how it behaves to verify if the particles are stable in environmental conditions. If we consider the fresh water, we can measure more or less this, a couple of clouds, more or less in the same position, and without any secondary population. The nice, interesting thing is that we are able to size them but also to identify an effective refractive index, which is in the middle between the refractive index of the lipid and the refractive index of the zinc. This is because there is an average within the contribution from the zinc and the contribution from the lipid. And from this information, since we are aware about the formulation, we are able to estimate a loading in terms of the mass of 30%. So that in terms of the mass, 30% is zinc, 70% is lipid inside this kind of particles. And this information comes from the analysis of the effective refractive index of the final formulation. Then we can move the analysis to the behavior. We can incubate the system in controlled situation and look at how the particles behave in time. After 10 days, as you can see, the particles in fresh water are more or less the same. The same happens for particles in medical water as well as for particles in pit bog water, considering different samples. But the particles in seawater start to change, and their change is complete after 20 days. So they shift the position of the clouds toward to an area corresponding to lower particle, to lower refractive indexes. While on the other side, the particles dispersed in fresh water are stable. This system shows us that we are able to observe and measure in a quantitative way the degradation of the carrier due to the interaction with the surrounding media. In this situation, due to the osmolarity of the liquid, the lipid particles are not more stable. They break and release the zinc oxide nanoparticles inside. So if you are looking to a biotech application and you have to check how the biotech particles behave after a release, for example, in the environment, you have to monitor how they behave in different target media. But you have to monitor also if they are stable, and if not, why. In this case, we are able to measure the behavior of particles from the point of view of the carriers. And in this scientific project, we collaborate with, for example, with a group with a differential centrifuge, SPES, and they measure the nanoparticles of zinc oxide after 20 days, but they were not able to measure in the same time the presence of the lipid particles. So we are looking at the same problems from two different points of view. We are sensible to the carriers, and we are able to identify the presence of differences in the carriers structure in time. And this provides to the formulator an information about the best surfactant and the best stabilization of the best approach to have a given release, for example, or given stability of the system in the target media. This can be done online, for example, coupling our system to traditional approaches. Let me show you an example coupling our system to a commercial FFF. Here we are measuring as a reference for some methodological validation a mix of polystyrene and PVC particles with the same size dispersed in the same liquid. And we are measuring in real time in line with an FFF, a spectrophotometer, and a DLS. This is the signal coming from the spectrophotometer. As you can see, thanks to the FFF, you fractionate the particles in time, and you measure a couple of peaks at different times. You know that the difference may come from the different density. But if you are not aware about the nature of the particles, you just measure something related to the absorption. But which is the particle which absorbs? How many particles per minute there are? There are more populations, so a contribution coming from different kind of particles. You can also measure the same system using dynamic scattering, for example, in this case. But again, you are measuring an average hydrodynamic radius about the total system, which is transit through the system at that time. So you are not sensible to the presence of more components, and especially you are not sensible to the structure of the particles. So you are not able to estimate the refractive index, estimate the contribution to the absorption of each single particle. So you are not able to really define the properties of the particles using these traditional approaches. Luckily, our system provides the missing piece to identify this kind of information. As you can see, also in our case, we are able to measure two different peaks or in terms of numerical concentration in times. So we are able to provide for each second how many particles per milliliter are in the tubing. So we are able to provide information about the numerical concentration of the particles for each single peaks. which is essential for a proper evaluation of the absorption, for example. But moreover, we are able to focus the analysis not just in terms of the position, the location of the particles in our three-dimensional plot, but also in terms of the time. So the user can select the time slot and retrieve the particle size distribution and the two-dimensional histogram of the particles present in the first peak, then the particles present in the second peak, and for the particles in the first peak, it is possible to retrieve the two-dimensional histogram, so to obtain information about the extinction cross-section as well as the polarizability of the particles, to quantify them in terms of the size, in terms of the concentration, in terms of the effective scattering properties, and the same can be done for the second one. And so we are able to say that in the first peak there are polycylindrical spheres of 1/4 micron, in the second peak there are PVC particles with the same size. This information, coupled with the previous one, provide a very nice overview about the problem. So more information give you more possibility to face complex systems. We provide a multi-parametric approaches. It is useful also to consider that we can join our forces and you can combine our data with traditional devices that maybe you already have in the lab. So we are the missing piece about your systems. Let me show you the last but not the least example about inline online quality control. In this case, for example, let me show you the typical data coming from a system of particles changing in time. We have a reactor in this case. As you can see, considering the numerical particle concentration in times, there are different events, and there is a huge one after 3000 seconds. And then again, there are different events here. As you can see, we can retrieve and plot the whole two-dimensional particle size distribution in terms of the clouds of the whole process, and we can observe the presence of different clouds in the media. But we can also focus the analysis to the particles in the peak, the giant one, and in this case we are able to identify a huge population related to an emulsion of oil. We have to say that it is an emulsion of oil because from the shape of the clouds, this means that we have particles with a very narrow optical properties, so precise spheres of the same material, with a polysparse particle size distribution. This is typical from emulsion. And plus, we are able to estimate in an automatic way, judging from the position of this line, the refractive index of the material, which is compatible with the oil used during the process. So in this case, there is a leak from the oil during the process. So it is an impurity. It is not a strong sin not coming from the particles of interest. And if we focus the analysis on a different time range, time slot, as represented here, we are able to appreciate the presence of other populations. There is a first populations related to the electric particles, for example, in this case, but also a secondary population related to absorptive particles. In this case, they are the carbon particles. So you are able to identify the presence of two kinds of populations, quantify them and size them. You are able to quantify the changing kinds in terms of the numerical concentration of the single populations, but also in case of the presence of an impurity, to identify that impurity is not just an increase in terms of the concentration of the standard population you have, but is something more, it is something different. So it is a third population related to the impurity, which arrive in the fluid and flow through the device. So you are able to monitor. The monitoring in time can last for all the time you like. The only limit is the hard drive, because we measure and save in real time the information for also hours. So it is not a problem to measure also long synthesis, long processes, and to analyze the data later offline, but measuring inline and analyze the data offline. As the last but not the least in terms of the applications, let me show you the capability of the system in terms of batch-to-batch analysis. The SPES data is a multi-parametric data, so we provide the two-dimensional histogram. And we can benefit from different statistical approaches developed for the analysis of images. As the first one, we develop a special principal component analysis based on SPES data thanks which we are able to identify the presence of secondary population in a multitude of batches, or in a better way, we are able to create parameters and quality regions and estimators, thanks which we are able to classify batches as good batches, bad batches, and third batches related to an already existing library of data. So in simple words, if you have good batches, you measure the good batches with the SPES, then you measure bad batches with the SPES. This information, this statistical information, is able to provide you a quick interpretation of new batches in terms of how they are different to the good one, how they are different to the bad one, or if there is a difference in terms of third populations not present in the previous ensembles of data. So it is a very powerful analysis tool with high potential in terms of batch-to-batch analysis from the statistical point of view. We published on the website different application notes. There are different links to published papers about the method, but for sure, the first point of contact for any information, for any questions about the techniques, about the capabilities, about the applications are us. So feel free to contact us for any information, any question. We will be very happy to try to help you and to give you some information about how our system can provide you a support for your applications. Inventec is our local partner and distributor for the Benelux area, and for the German people, but let's say all the people that the next week are at an Analytica trade show, consider that we will be hosted by our German distributor, Quantum Design Europe, and we'll be at Halle HU at the stand 331 with a system, so you can come, touch it, and ask us whatever you like. We will be there for all the days. Thank you very much for your attention.
Thank you, Tiziano. Can I, well, there are already some questions for you in the inbox. Sure. Yeah, but I would first like to say that we will, of course, send you all the presentation and the recording afterwards, because it's a lot of information to process, I imagine. So that's what we're going to do after the webinar is finished. But first, a few questions. Maybe you already answered this one because it was asked really early in the presentation. Do I understand correctly that the particles smaller than 100 nanometers cannot be determined?
Yes, the system is not sensible to particles smaller than 100 nanometers, and it is not sensible to particles larger than 20 microns. This depends on the material, of course, because it depends on the refractive index and the scattering properties. But the pulse shape analysis implemented in the method reject all the spurious data coming from smaller and larger particles, so no artifacts. In case of a high concentrated system, some alerts and error or suggestions are provided to the user to best manage the sample and the acquisition.
Okay, well, thank you. Well, if it's not clear to you, you can always contact Tiziano, of course, for more information, but I have more questions. I have to see where I got them. Okay, here. Another question, can we also measure liposomes by with this technique?
Yeah, we have experience with liposomes. Let's say, depending on the sizes, we are able to measure them. We have experience with large liposomes, with the multilamellar liposomes. We were able in the past to estimate the thickness of the shell of the liposomes on the basis of the shape of our clouds. And in case of some API inside the liposomes, if the API changed the average optical properties of the particles, we are able also to estimate the payload. So depending on the cases, yes, we are able to provide very nice information about these kind of systems.
Okay, well, I would surely contact Tiziano for more information on that one. Yeah, I have another question. How does agglomeration of particles affect the results?
Yeah, we have to consider the particles as a very strange object in terms of how they interact with the light. If we consider a very compact sphere as a reference, the refractive index of the particle is the refractive index of the bulk. So we can measure without any calibration the refractive index of the materials as presented in the literature, for example. If we have an aggregates, the refractive index of the aggregates is not the refractive index of the monomers which compose the aggregate, but is an average between the aggregates and the liquid between the monomers of the aggregates. So we are able to measure a refractive index which is lower with respect to the bulk, but is the most useful one for a proper sizing. But also looking to the aggregates and looking to the effective refractive index, we are able also to estimate the compactness of the aggregate. Let's say we are able to identify the relative percentage of the mass of the monomers or the volume of the monomers respect to the total volume of the aggregate. This is very essential if you have to tailor a formulation to reduce the number of aggregates in suspension, or if you have to monitor the aggregation ongoing in suspension. In the last month, we published the papers and a application note about this capability. If you give me the time, I have just a very, very quick example for you. Let me show this. As briefly described by Word, if we consider an aggregate, we have to face the scattering from the whole system. So monomers and the structure of, let's say, the ensemble and the arrangement of the monomers inside the aggregates. So, for example, in case of aggregates of titania, we are able to measure refractive index lower respect to titanium. If we sonic the system, we measure a refractive index higher respect to the previous one, because we are destroying the aggregates, we are breaking down the aggregates, so the particles in suspension behave more like the monomers. The same in case of the carbon. If we sonicate the black carbon system, we can measure the typical class of an absorbing material. If we leave the system, we are able to measure the aggregation ongoing and the increase in terms of the size and the decrease in terms of the effective optical property. So different estimator can be provided in terms of the characteristics of the structure of the aggregates in time and in complex formulation. Let me give you another example by Word. I don't have here the data. A few years ago, we supported the analysis of a drug. The drug was composed by an API and 2 excipients. The real problem there was the stability of something inside this complex formulation. We measured the single component of the product, let's say the API, the excipient number 1, the excipient number 2 alone, dispersed in purified water, and the 3 components were stable. In the mix, something changed. In the mix, due to the interaction between the particles, the API was not more stable and tend to create larger aggregates passing the time. So in the end, we found out that the clouds related to the signal coming from the API shifted toward larger sizes while we are measuring it. So we are able to provide information about the stability and also information about the particle-to-particle interaction in that case.
Okay, well, thank you. Well, I hope, yeah, because the connection wasn't that good, so I hope everyone was able to hear everything, and otherwise you can always send in your questions. I have another one for you. What is the beam waste size needed to sample single particles?
Depends on the size of the particle. The system has 2 different optical lines for the analysis of particles larger than 1 microns and for particles smaller than 1 microns. We can say that the size of the beam is a few microns for smaller particles and few tens of microns for larger ones.
Okay, and the CFA done online or as a development exercise before production setup?
Both, I have to say. Considering some installation of CFA, of continuous flow analysis, some of our customers use it for Inline, online analysis, coupling to other systems. For example, you have a stream of particles. You want to measure the same stream using different methods in real time or on the same line. So you can measure the particles with a system number 1, then the flow go to the system number 2, then to our device, to another device again, and so on. So we are in the middle of a complex measurement system. Or another application is the analysis of particles in small pilot reactor system. For example, the system can be used as a sensor to provide information about the characteristics of the particles. And in the past, we applied this for some predictive interpretation of the synthesis. For example, if you know that the shape of the clouds of your particles changing time, changing some of the characteristics of the process, you are able to monitor if the shape are changing the right way, and you are also able to monitor if not. And if this is the case, you can in real time change some parameters of the synthesis, for example, to monitor the change of the particles, to, let's say, to increase the yield of the, for example, synthesis, and to check how the particles behave. Another process can be the definition of the optimum of a process. For example, if you have to mill something, you can measure the size of the particles and the numerical concentration of the particles in real time to define when they achieve the right size and the right concentration, for example, to not waste time during a process. So different approaches can be done and can be attempted using our device Inline online.
Okay, great. Thank you, Tiziano. That were all the questions. Well, I'm very curious what bio-based or biotech inventions SPES will bring in the future. I'm going to well, close down the webinar at this moment. And thank you again for your great presentation. And okay, I will send you all the presentation or the webinar afterwards with the presentation of Tiziano.
Thank you for the interest in our method. Feel free to come back to me for any further question. Feel free to ask whatever you like. If we can provide you a support, it will be a pleasure again.
Okay. Well, have a good time. Thank you. Bye-bye.
Have a good time to you all. Bye-bye. And see you next week to who will be at Analytica.
Bye.
Bye.